And I kind of, started thinking one. Good
afternoon, or good noon, everyone. Welcome to the College of Education. I'm Donna Weissman, the Dean of the College, and I am particularly excited to see all of you here today, and I'm excited to be part of the welcome for our speaker, Rick Duschl, who has Rick, did it feel like you were coming back to class when you walked in the building? And I don't want to steal, I know Randy's going to do a formal invitation, but it's really wonderful to get together and to listen to someone who brings us ideas that we need to think about, ideas that make us uncomfortable. I don't know if you're going to do that, Rick, but ideas that make us really think about the future in education. I have a feeling that Rick can get us thinking and talking about all of those things today when he's talking. That's really what it means to be in the university. So it's really wonderful to see all of you here, and we do have some little munchies over there, so you need to get something, go ahead. So welcome to the College of Education, and with that I'm going to turn it over to Randy McGinnis, who will introduce our guest for today.
Thank you very much, Donna. I always thought that the best person to introduce a speaker is a very short speaker, and so I have very brief remarks to make. What I really wanted to say is thank you very much for coming. This is our inaugural talk for our renamed and repurposed center, the Center for Science and Technology in Education. And we had a big issue of thinking of who we would want to bring in to be our first speaker. And of course, the name that came up on everyone's mind was Dr. Rick Duschl. And one of the reasons is because he's a graduate of this place, and we thought we could actually convince him to come over. The other is he's local right now at the National Science Foundation, so we assumed that may be possible. And it did work out. And what was nice is that when I contacted him, it was a pleasure because he came back immediately and said, I really, really want to do this. What's been taking you so long to ask? But just to put it in context here, his talk is one on STEM. And I don't know if all of you have looked at our latest faculty voice in which our chancellor has identified STEM in a timely way. In fact, the title of Britt Coleman's piece is called Defining Maryland as the STEM Capital. Now, we have a lot of advantages in our university system, and we have a lot of intellectual resources along the way. But we really need to have guidance in this. And so our speaker, a person who graduated from the University of Maryland, an undergraduate, a man who took his doctoral degree here at the University of Maryland, a man who is recognized as one of the premier graduates of our institution who did well, is here to speak from his position as someone who has been a great leader in our field related to this whole notion of rethinking science education, teaching, and learning. I don't know if all of you have ever looked at the 2007 book on taking science into schools, one of our big books. Well, Dr. Duschl was the one who was in charge of that, and I think had a big influence in looking at an initiative on learning progression. So in all of this, it's my pleasure to have all of you here, and of course, our speaker. Please, Rick, come here.
Well, thank you very much for the warm introduction. And it is indeed a pleasure to be back. And I thought I'd begin the talk by talking about where I went after I left here in 1982. Now I got back here in 2013. Wow. So in '83, I did indeed graduate from the University of Maryland with my doctorate in the Science Teaching Center, which is in the basement of this building. And John, as I was walking down, and I was telling Randy, I said, yeah, we were in a basement, and people learned quickly that you didn't put your books on the outside wall. Because during heavy rainstorms, the water did come in. That's a good thing. In '83, unlike today, there are only 3 jobs offered. Rochester, Wisconsin-Madison, and the University of Houston. I was fortunate to get the job at the University of Houston. And so I left there with my family, drove halfway or more across the country to the first of many places, those of you who know my track record. So I was in Houston for 4 years, and we were desperate to get back to the East Coast to be closer to our family. So I took a job at Hunter College in New York City. When I arrived, Duschl left, and when Duschl left, House of Cards fell down. And all the deals that had been made and struck sort of evaporated. My first big lesson about higher education, get it in writing. And then from there, I went, and out of behind every dark cloud, there's a silver lining. I took up a position at the University of Pittsburgh. And it was a great opportunity for me because it was the first time that I really found myself at a university that, one, had one of the highest recognized programs in philosophy of science, the Center for Philosophy of Science, which those of you who know me know that that's one of my key interests. But then I also had the Learning, Research, and Development Center. At that time, probably the premier institution in the world, certainly part of the country, under Bob Glazer and Warren Resnick's directorship. And although I was never a member of the ORDC, I forged many effective and long-standing collaborations, the most significant of which is working with Leona Shabla, where we did our NSF work in classrooms together there. I was then wooed to Vanderbilt University from Pittsburgh, and had the pleasure of working with the likes of Jim Pellegrino, John Bransford, Paul Cobb, just stellar individuals across there. Then the big move, which was across the pond to King's College London. And when I was contemplating going to King's College London, a colleague of mine at Vanderbilt, David Bloom in language arts, had a colleague from England, and I sat down with him and I said, why should I go? What's the deal here? And he said, well, my understanding is that when people go to England, or when British go to the United States, they come back being seen as a more highly valued kind of commodity, if I could put it that way. And so this list is what I sort of think going to England got me. Is that people thought that perhaps having had the opportunity to work with people like Paul Black, Jonathan Osborne, Dylan Willem, and many other scholars there, Stephen Ball, those of you in sociology of science. I came back and I was given the opportunity to be part of the planning team, the white paper, and then stayed involved with the NAEP 2009 framework through its entire development. I went to school on assessment, and I didn't take any classes. I lived it, which is an interesting way to learn something. As Randy said, I had the opportunity to chair the report in 2007, Taking Science to School. I was invited to be one of 4 members of the AP Reform Learning Sciences panel, and I did so in my disciplinary hat, which is the earth sciences, so representing the earth science community. I then had an opportunity to work with the New Jersey standards when I was at Rutgers. That was the place coming back from England. I also recently worked on the NSF Geography Roadmap project, being a member of the research committee. I, on the leadership team and co-chaired the Earth Space Science writing team for Next Generation Science Standards. And then that gave me entree to another group, which is the Building Capacity in State Science Education, which is a breakaway group, yeah, it is kind of a breakaway group. In writing the Next Generation Science Standards, it's 26 lead states decided to sign on and sort of take the process forward. Those 26 lead states came together and said, we got to start planning now and get out front on all the professional development challenges, on all the adoption and implementation challenges that will be taking place. And now, as Randy said, I'm at the NSF. It's kind of it's a golden opportunity for me to be at NSF because I've helped generate the agenda that is now at my desk. And one of my problems is that I'm being told to say, you can't be such an advocate for these things. You work for the government then. You can't show your hand, So I don't endorse the Next Generation Science Standards as much as I endorse the 3-dimensional approach to the teaching of science. So, you have to couch it in sort of the language that's there. So I'm going to build my talk today around and draw heavily upon 4 recent publications. From the bottom up, I got an opportunity to pull together a lot of my thinking that has developed over the years, which is to say that the teaching of science is complex, it's multidimensional, and we've had a tradition over the years of just focusing on kids learning the concepts and the conceptual meaningful learning. And when we take a practices approach, there's other things that have to come into play. So I wrote an article called Science Education in Three-Part Harmony, Balancing Conceptual, Epistemic, and Social Learning Goals. And by social learning goals, what I mean by that is really fundamentally the critique and communication of ideas and information. So within science, when we think about how science knowledge builds, it is not built slowly by individuals. It must always go out to the public for a conversation about the ideas. And how do we begin to get those practices into the classroom? In 2011, I got an invitation from the editor of Studies in Science Education, Jim Ryder. Would you be interested in helping us? And this follows on from what Randy said about the Taking Science to School, that had a chapter on learning progressions. Would you be interested in telling us something about learning progressions? And importantly, I added in teaching sequences, because that's the language in Europe. And this is a journal that is published out of England. And so I wanted to make sure I was connecting to the two communities. And I had the opportunity then to review and do an analysis of what is a very beginning field. And I want to emphasize that there's a lot of people engaged in this, but there's very little that we actually know. And same thing, and this field, as it begins in the article, builds off of, and I see Dan in the back, you know, from the math trajectories, from the math communities, because they were out in front with that process. Had the opportunity with Richard Hamilton to contribute a chapter that Richard Mayer and Patricia Alexander had invited to do the chapter on learning as it related to science. And then my other, you know, as I said, Nature of Science, had the opportunity with Richard Grandy to look at competing perspectives about the teaching of the nature of science in schools. So 2012 was a hell of a year. You got to know this. If you want to be successful, I would argue these days, particularly successful at getting funding at the National Science Foundation. Because they help set the agenda. So the 2012 Monitoring Progress Towards Science, Successful STEM Science, is the blue book that follows on from the orange book that's just called Successful STEM Schools, which was a program mandated by Congressman Wolf, who ironically, NSF is in his district. And he's very passionate about wanting to have more knowledge, more funding, and sits on the right congressional committees to make sure that we get the job done. So when he calls the tune, we dance. And what he wanted was a follow-up report. He said, well, this report on successful STEM schools is great. Now, how will we measure it to see if we're making progress? So in that report, you're going to see a recommendation of 14 indicators. Of those 14, 6 are tabbed as being a priority, do them earlier rather than later. The indicators are very important to us, and we're trying to think about how we build out the knowledge base in STEM education around the indicators. So look at that. Jim Pellegrino seems to never leave Washington, D.C. Yet another report by him. He did earlier on, he led the Knowing What Students Know report. But this Education for Life and Work takes on the challenging topic of what do we mean by deep knowledge? And in that book, and I'll show you in a moment the features of that. I've been joined a couple months after I arrived at NSF. Tomorrow's my 1-year anniversary. Unbelievable. But Susan Singer, who is the lead author of the disciplinary-based, or the DEBA report, is now the director of the Division of Undergraduate Education. And then, of course, the book that led to the actual framing of the Next Generation Science Standards, the framework book. So in Jim Pellegrino's volume, the NRC, you know, he talks about cognitive competencies, intrapersonal competencies, and interpersonal competencies. And think about those as practices. Okay, think about those as practices, right? You gotta learn to talk to people, you gotta learn to be critical of your own thinking, you gotta be able to engage in the reasoning, and the communication, and the argumentation. And what goes along with this, and what's another big fertile ground for research and development, is what are the performances, since these are practices, what then are the performances that you would want to have learners do, adults do, children do, that would indicate that they are indeed making progress, learning progressions, they are making progress on the component parts of what it is that you want to learn. So, we're waiting with bated breath any week now for the next NRC report to come out on assessment. The DEVA report targets undergraduate education. Speaks an awful lot about the need for developing a new community. So Joe Reddish is squarely in that community in my mind. And trying to understand how people learn the concepts, the practices, identifying and measuring instructional approaches that support, identifying approaches that are more inclusive of all students to try and grow things out. So what's interesting to me to discover being at NSF is that while there's a vibrant community of faculty at universities and colleges who are interested in this, it's still the case that back home at a research-run university, it doesn't pay the rent. Right? Yeah, no, it doesn't pay the rent. And so how do we get to the other side of that? How do we begin to get the rewards? Now, a place like Maryland that had a science teaching center that had like John Lehman and all my faculty members when I was here all had joint appointments between this place and respective place, and it wasn't just in science, it was in math, it was in history, it was literature, but that sort of evaporated away as the initial leadership, in this case John Toll, the president at the time, really made that center come to life. It kind of eroded over time. So do we get back to that? But this has a lot of recommendations on how we're going to build a new research community around discipline-based education and research. So going into the Taking Science to School report and the framing for the framework and then for the next generation science standards is to look around these 4 strands of science proficiency. And the two in the middle, are about sort of what I'm going to say in terms of rolling this out for classroom teachers. I've learned from speaking with other people that you can't make it so new that you don't understand what you're being asked to do. You got to build off of something that's comfortable. And I think the thing that good science teachers, and given the fact that we've been touting inquiry for a long, long time, and now the shift to practices is really just sort of opening up the flower. It's sort of saying, it's inquiry, but what are the components of it? So reflect back on the competencies, cognitive, intrapersonal, interpersonal. Most people wouldn't put all of those into, say, what's going on in inquiry. It resolves in, basically, well, you're doing a hands-on activity, you're doing an experiment. It's not the communication, the refinement, the building, the iterative process that we know is a major part of building ideas. Just a second, let me get through that, I'll come to you in a second. So when we look at the framework writ large, we got practices, cross-cutting concepts, and core ideas. And I want to pull out just for a second the planning and carrying out investigations. Because for me, I see that as perhaps the best entry point for classroom teachers to begin the process of beginning to think differently. And let me show this slide and then I'll take your question. So that, here are what I think is some of the components that could be a part of planning and carrying out investigations. And these are things that are not givens, and that's part of the problem in a lot of the classrooms is that the activity is given, it's pre-planned, it's packaged, the questions are determined a priori, and it's all driven towards a demonstration of the concepts that we think are important for children to know and learn.
Where does analytical thinking or reasoning, in particular using arithmetic and algebraic calculations?
Yeah, so back here, right here, using mathematical and computational thinking is one of the practices that we want to weave into it, okay? So, you know, I'm pulling this out by just making the argument that if I'm going to start a process with teachers in a school district, and I want to get them to think about the coordination now of this. So the agenda for this is to use knowledge, not to know it, to use it, practices, performances, so that when you look at the framework and then the next generation science standards, you're going to see statements written as performance expectations. That given this, you'll model that. Given this, you'll engage in the computational thinking about that. Yes?
So I browsed through the NRC's K-12 science framework, and my impression was that mathematics simply meant statistics, and that in general it was arithmetic and algebra calculation avoidance document.
Well, that's a good start for K-8. Quantitative reasoning up to the 8th grade is a good start to get us going. But if you read forward now to the next generation standards themselves, and I encourage you to do that, you're going to see at the bottom of each of the templates links to the math program, links to the math standards. So the math is there. But you're asking the wrong person about the integration of math into this. I chaired your science committee.
Which science?
Earth. Yeah. So deciding, developing, documenting, devising, determining, again, practices that lay out the sort of the give and take that takes place in a conversation around conducting and wanting to know and build models, devise experiments, and engage in that process. So all of these things, in my opinion, are involved in generating evidence. And that's part of the doing part that we want. We want the students to go through the process of the conversation, again, interpersonal, of thinking about these kinds of things. We typically don't make this a decision point, right? You know, what data to collect? How long? When do you know to stop collecting data? What are the, you know, how do you structure the data? This moves us towards the analytical thinking, towards the ability of beginning to look for mathematical patterns within things. Joe?
I like all of these items, and we work hard trying to get them in, but what I'm missing, and what concerns me about in presenting them like this, and I haven't looked at the actual report.
Oh, this is not the report, this is my list.
Yeah, okay. Is that if I'm a teacher and I'm looking at this list and say, I have to have students to do this, I have to have students do this, and so forth, that what's missing for me is each of these are in the service of.
That's right, it's organic.
And how do you get that?
Well, I would argue you get that
describing.
through the complexity of a problem, that it's embedded within a larger problem, a problem-space scenario, a design space scenario.
But the teacher has to perceive that.
Oh, absolutely. Not only does the teacher have to perceive it, the challenge to the teacher is the teacher has to know what the end game is, right? They got to know the pathway. They got to know the progression. And they got to know, and this is where we begin to talk, when we talk about pedagogical knowledge or teacher knowledge of a discipline, it's not just the knowledge of the discipline itself, it also has to be the knowledge of how people learn that discipline. And how to give that effective feedback, because that's not a lot of this agenda isn't going to happen unless the teachers in the classroom are prepared to give the feedback that's necessary. Now, in order to give the feedback necessary, they need in their hands the performances that make thinking visible, that allow inquiry to be obtained, in a sense. So in our chapter on science that we wrote on learning, and again I want to reveal a little bit about my passion for how philosophy of science comes in and helps us answer some of these questions about the pathway and what we have to pay attention to. This book by Carruthers, Stephen Stitch, and Siegel is a book on the cognitive basis of science. Is the title of the edited volume. And the introductory section is one of the most concise, best summaries of what has happened over the last 50 years in philosophy of science, what has happened over the last 50 years in cognitive science, what has happened over the last 50 years in philosophy of mind. And pulling, and then demonstrating how these are pulled together in two conferences, one that took place in England when I was there and I got to attend that, and then one that was back on this side. Stephen Stitch was at Rutgers, and so I had the opportunity to come back and be here for that and got to see that. And so it was bringing together scholars in each of these communities to talk about the cognitive basis of science, both as it occurs within individuals and as it occurs within groups and communities. But it was also, how did science begin? So there were some interesting anthropologists there who are actually going way back to 30 BC and looking for evidence of scientific and mathematical reasoning in the ruins that took place, and how do we begin to look at that? So, thinking about shifting the idea about thinking about what scientists ought to do rather than about what they actually do. Okay? So Joseph Schwab wrote about that in the late 50s, about looking at, from a philosophical perspective, he started to ask, well, what are the behaviors of scientists, is what he called them, to sort of set it out as being slightly different from what the psychologists did. It is important then to see science as a natural phenomena, somehow recruiting a variety of natural processes and mechanisms, both cognitive and social, to achieve its results. So again, we see that in the ocean of practices about social communication. What makes science possible? Specifically, what features of human mind, human cognition development, and human social arrangements permit and facilitate the conduct of science? So when I look at stuff like that, I say, okay, so how does that play out in the classroom? What's the social arrangement? What's the cognitive development at that particular period of time? Because it's a community, and now with a lot of the tools that we have, we can link these classrooms in a way that can really sort of ratchet up the ways in which we have children talking to each other, arguing with each other, debating with each other, investigating with each other. Such questions are interdisciplinary in nature, referring to these, requiring cooperation between philosophers, psychologists, and others in the social and cognitive sciences, as much about the psychological underpinnings of science as about the science itself. So what does that say to me? It's teamwork. It's teamwork. And this is what has drawn me and many others to the emerging community of 10, maybe 15 years old of the learning sciences. And that's not embraced by everyone, as we know. And I've struggled in 2 universities to try and get something stronger going in that, but people like their comfortable shoes and want to stay where they are. But I hope the next generation begins to think about the fact that, the problems that we have to address with respect to the coordination of those 3 dimensions, practices, concepts, cross-cutting, we need, you can't just come into it with one discipline and figure that out. You got to have multiple ideas and people working together to take on. Someone has to know the discipline knowledge itself inside out. Someone has to know how people learn at that particular age. Someone has to know how to begin to provide and write the assessments that are going to get the performance out. I mean, so these are complex labs in my sense, and that's a challenge for us to begin to move in that direction. You had a question? Oh, I thought it was my hand. So a lot of the ideas for practice come from this. Andrew Pickering is a historian of science who wrote some very influential books on understanding the cyclotrons and the experiments that are done with high energy physics. And in his book, he talks about this idea of a mangle of practice. And he talks about the fact that there are 3 elements. You've got to get the materials together. You got to think about an instrument model, and you got to have a model of the phenomena. And that's just for the start, because the hard work is how do you coordinate all 3 of those things together. And so a good article to look at in 2008 by Michael Ford is, this was a framework he used for his dissertation. He was a student of Leona Schaubel's. And so Leona and Richard Blair have taken this on very deeply in thinking about these practices approach again. And when you look at the introduction of the first handbook of the learning sciences, Keith Sawyer, summarizes this idea about practices is that one of the ways that the field has been doing this is going to look at professionals who do that job. Okay, so if you want to be a statistician, how do statisticians actually go about doing the work that they do? So Rogers Hall, for example, has done a lot of interesting research in that area. But that's one of the ways that you get a toehold on sort of, okay, so what's the game here? What are the suite of practices that we need if we're going to have a progression towards moving towards that? And then you begin to go out, and I'll show you with some of my own work at the end, is then you begin to find out, and you say, okay, where can that appear? Where can, because we know that young children, and that's one of the biggest messages from taking science to school, is kids are a hell of a lot more capable by the age of 5 than we have ever given them credit for. And so when we have a different platform from which to begin, and we understand how to move that forward, hold on to your hats when we get the kids to middle school and high school.
I think there's a phrase that has changed all this.
What's that?
What is your evidence?
Yeah.
And that is something that is associated with children at all levels now without an apology. And it's what you're neglecting the scientific method in your discussions today,
Oh no, there's evidence behind this.
Oh, well, but leave it at evidence. But fortunately, we don't hear ourselves talking about the scientific method.
Well, it's a different model here. There's a method here, but it's not lockstep.
It's nice
Now there's other slides that I should have put in there for this. But so this leads to this idea of learning progressions then, right? If we have this complex set of practices and we want to begin to think about it, these are items taken from this book, The Taking Science to Schools. Traditional instruction does not enable most children to attain a good understanding of scientific frameworks or practices. But there's evidence that the proposed learning sequences could occur with appropriate instructional practices. So the example I like to give when I talk is FOSS kits. Okay? So elementary schools, FOSS kits, expensive. You buy a set, maybe 2 at best. And you buy a set or 2 for each of the grade bands, K2, maybe 3-5. And each teacher starts off with a kit, a different kit. And then they swap as they go through. It makes no sense. It makes no sense. What do you build off of? How do you coordinate this idea of a sequence? Okay, so the more effective instructional practices aims to build understanding to involving students in a way of practices, but to do so in a way that coordinates them from one place to the other. So the progression is not just about concept learning. Importantly, it needs to be about that. But it also needs to be about the development of the reasoning practices. Where do you start with third graders, fourth graders, on developing the work towards statistical processes and analytical reasoning? And we have the math. There's math research that shows us how to get that done. Jim Caput, has it's pioneering work on how to begin with fourth graders, the basic precepts of calculus. And so, we're making progress in these areas. So from the review that I did for the learning progressions, I found that there's kind of 2 generic approaches. Of course, we were force-fitting a lot of this, but a validated approach says that I have this curriculum, I have this project, I have a way of thinking. Let me go out and validate that this is indeed a progression to follow. The example that I give here is the AAAS roadmap. Okay? That's a given. That was crafted together by you and I, very smart people, said, well, yeah, you should start here with this topic in kindergarten, and you should go up. Now let's go in and validate whether that's the right thing to do. Okay? The alternative is what we refer to as an evolutionary is that you're not validating, but you're actually getting in there and testing out careful sequencing of teaching experiments across multiple grade levels. So you're finding out, you know, what the boundaries are, what the limits are. Because here you're making a lot of assumptions. It's theory driven and top down. This is data evidence driven and bottom up on learning. The upper anchor here, in other words, where do we want people to end up when we look at most of these, is we want them to be college ready. The upper anchor here is as targeted or adult literacy, right? So we have college and career readiness. How do people, you know, move? Not everyone goes to college, but a lot of people go into careers, and how do we work towards that? Use assessments to confirm the learning models. Use assessments to explore learning models and build them. Progress variables, steps, and targets are fixed. So Mark Wilson has come up with, he's doing a lot of the key work on measurement. And in his theory of measurement around learning progressions, he'll say, well, what are the 5 variables or concepts that are really important for developing deep understanding in this domain? And then he calls them progress variables. Okay, so an example well, one of the first learning progressions was on matter. And how do you move from a macro to a micro understanding of the features of matter? And what would be a variable that you might follow through there? So you might say, well, how does a child's understanding of what a molecule is change with time? What is the concept of energy? How does that change with time? Concept of matter, how does that change with time? Over the course of years now. That's the thing that's amazing about this is asking questions about what can we do over multiple years, not multiple days, multiple weeks, but multiple months. Now we're starting to talk, because that's where that teaching sequence model comes in. So that's another thing to figure out. So the progress variables here are fixed. The progress variables here are flexible. This is a big one for me. I see a lot of people who think that, you know, this idea of misconceptions, we spent 30 years on this in the field. And I meet a lot of teachers who say, oh, no, I gotta fix it. I can't let them go out thinking like this, as if they could fix it. Yes. And we know that, you know, as people go into adults, they still carry these same misconceptions and baggage because they're easy to trip up on. So part of the answer here is that it's not about, and Andy DeSessa and Jeremy Rochelle wrote a nice paper on, it's not about misconceptions, it's about intuitions. So the glass is half empty or it's half full. It goes back to what I said earlier about the teachers need to know how children learn the ideas and what the difficult steps are. So if I can ascertain, you know, something about what they know. So Brian Reiser one time in talking about this, about, you know, where does the moon go at night? Right? How do we explain the moon? You ask a little kid, oh, it goes behind the mountains. Oh, it goes to sleep at night. You know, and Brian said, well, it goes down the mountains. It's great. At least it's moving. I got an intuition to build on. So how do we monitor that movement now? You know, so that was kind of a tongue-in-cheek responsibility there. But a good teacher now, through these performance assessments, needs to figure out, you know, okay, so what do they got? What don't they got? How do we move forward on that? And Taking Science to Schools builds that out a lot. So theory building as conceptual change, model building as conceptual change in terms of grow the target on models, and then importantly domain general versus domain specific, kind of an orientation towards that. So we have a new view of the nature of science, and there's this debate in the field right now that if you read the framework, you'll see that they say the nature of science is embedded within the 3 dimensions. But there are people who have been doing research for 20 years on looking at kids' understanding of the nature of science. And so this is where Norm Letterman and I start to draw swords, so to speak, on what what actually counts as an understanding of the nature of science. And so, you know, if we look at the nature of science as it is expressed through the doing, through the practices, and then we have the evidence of how children, you know, go through it. Do they understand why we refine, why we generate mechanisms, why some things stay, why other things go? We think that that's a good measure of qualities of the nature of science. Let me go through in short order now a set of challenges that I think the field needs to consider. We need a common language. We don't have it about almost anything. And I'm not making any of those words up. Those are all from the literature. That they're categorized within certain areas. So how do we get to a particular language? Again, as a student of history and philosophy of science, I know that in the history of science, there comes a time when the scientific community said, enough! And they have this big meeting, which is called a union. And at this big meeting, they finally begin to say, this is the measurement that will count for that, or this is the name that will count for this, and this is the process that will do for that. You know, so if we're going to be an international community, we have to begin to deal with that. Challenge number 2. This is in 2-part. And this draws from the work of Bob Glaser. And so it should say, put the word psychology after cognitive. So in 1995, Bob Glaser gave a presentation at an international conference, and he said, here's what we know makes a difference in instruction. That we know that knowledge is structured, we know that prior knowledge matters, we know that metacognition is important, and we know that procedural knowledge has to occur within meaningful contexts. It can't just be because it's the next thing in the book. But coupled with that is a set of social psychology practices, that there is a social participation in cognition, there's a holistic situation for learning, and that making thinking overt becomes very, very important in terms of what we have here. Now, you know, these things are not domain general. They can be. I mean, so metacognition, right, will have sort of like, well, self-regulation, self-efficacy, beginning to look at that, and that's important. I mean, but we're now finding out that the context matters, and that goes up to another deeper knowledge about the structure of the knowledge itself. And again, look at the fact what I said before, we've always had to focus on conceptual structures. But when we add in the epistemic structures, that begins to complicate. We need more research in this area. Models of learning. The literature on formative assessment, largely drawing on cognitive approaches to learning as individualistic information processing, has tended to ignore semiotic theories of disciplinary meaning-making, epistemic theories of how science knowledge is produced and validated, and sociocultural theories of the role of the group participating in the learning. And so when we begin to tease these out, Drew Tomer and I pulled these out, and we sort of said that, well, if you look in the cognitive, and this, this drew heavily from Bob Glaser's list. If you drew from the epistemic, we have somebody, and I apologize that that's off the thing there. And then from a sociocultural perspective, these become the dynamics or the elements of what we have to look at in coordinating how we want to change our instructional environments, our learning environments. So, challenge number 3. Assessment. Lovely chapter by Paul LeMahieu and Riley that appears in the Mark Wilson book, NSSE yearbook of 2004, taking up questions of assessment. This is at 2 levels of scale. This is at the school level, the system level, where superintendents and state boards make policy decisions about what they want schools to do. And this is what's happening in the classroom. This is what's happening in the classroom. So And it's different in so many ways. Not the least of which is sort of the timing of it all. You know how quickly this has to be turned around. The scope at which that happens. The targeted audience, as you can see here. And we need more attention to that, because one of the challenges is how do we get the assessments at the level of the classroom to be consistent right up to the assessments at the top. So it's called the coherence problem. How do we cohere the NAEP exams, the state exams, that will feed information to help the teacher do things differently? But what can the teacher do in the classroom that can actually feed information as to how children are doing? Challenge 4. Extending and scaling the research into instructional practices. So we talk about aligning curriculum, instruction, and assessment. We're talking about learning progressions, formative, summative assessment, instruction-assisted development, adaptive instruction, mediation of learning, and a new hot one is ambitious practices for teachers, beginning teachers. A lot of this is happening in greenhouses. And it's good stuff. We know a lot. But how does it get out? And so one of the things that is a new emerging field is another DBER, not design-based, disciplinary-based educational research, design-based implementation research. So Bill Pennywell, the new Tony Bright's work on network improvement communities. If you don't know about that, look it up. It's the next great thing. It's rapid prototyping of research. Don't tell me you're going to wait a whole year before you teach your unit again. Stagger it throughout the year so you can get several iterations and learn a little more quickly as to how to give the right assessments to kids. So it's this rapid prototyping. Failure's not a bad thing if you're learning from it. So stretch it out. So there's different models that we need to have here for that. Challenge number 5, extend, and this cuts to your question, sir, about data, constructing statistics. Data modeling needs to be integrated with inquiry, data, chance, inference. Richard Lair has a great program with Cliff Conolf and others, and been discussing with that and trying to come up with a progression from K through 8. The plea has been, and this is an important element of quantitative reasoning, and it needs to have a home, and it'll be in science if it can't be both in science and math. But I'm a big advocate for bringing those silos down. Challenge number 6, let me get through the challenges. Extending and scaling the research on attainment of epistemic communities of practice. Okay? So, these are all ways in which we express knowledge and formulate knowledge. We develop models and mechanisms, we have stories and explanation, we establish criteria, and each of these things have values behind them, and they have to be embraced by a community to get legs. And so how do we begin to push forward on those elements as well? So real quickly, let me just race through a study that I'm still involved with. Clark and I got a grant from the National Science Foundation to look at model-based reasoning in middle school students. And this was the research reported last year at NARST by my doctoral students and I. So the research objective was to generate and evaluate scientific evidence and explanations, to develop assessment criteria that would guide us in how to give feedback and understand modeling and mechanism-based reasoning, and then informing a coordinated teaching sequence or beginning the process of thinking about a learning progression. So we were guided by the assessment triangle that comes from the knowing what students know, that you've got to give you've got to have a task that produces an observation. You need to have a model of the cognitive
goals that you're looking at, and then you need to develop inferences or interpret the data you get. With respect to mechanism reasoning, we were guided by 3 articles from philosophers of science. Mockimer, Linley Garden, who is a colleague of yours here, and Carver, Paul Thagard, and Bill Bechtel are some of the people who have really thought hard about this idea. And I think the thinking about mechanisms is something you should buy into. So how can students be assessed on their mechanistic reasoning? What do such assessments tell us about students' ability to use evidence to make justifications? So praxis, that's probing reasoning and conceptual change in science. And so we had an iteration where kids got into a biology unit, they looked at cell models, and the question was, how does stuff get into a cell? What are the mechanisms for how things go into a cell? So we got thousands of student sample work over 2 years. We took 2 teachers, 5 classrooms, and started looking at a first year, second year kind of a model. And then we ended up doing a random sample of students' reports that were analyzed using the framework that we worked to develop. And we had sort of a high, low-end kind of models approach. And this is what it kind of looks like at the end. So we had 4 categories: modeling as it related to representation, argumentation as it related to claims, evidence, and justification, modeling as it related to explanation now, okay, not representation, but explanation, and then mechanism as an organizing principle. And it's a gross classification of saying, well, is this a high, medium, middle, and low in terms of what was there. And so we looked at the final models from 26 randomly selected students. High performance was judged to be a composite score, and you see the range there. And we got an iterated reliability of greater than 0.8 on looking at this. So this is an example of a low rating. So in the box below, show how you would think lead particles might get inside our cells. Use pictures and words, etc., to show your ideas. And so there's a statement here, and then some writing. This is an example of a medium rating. And you can start to see some qualitative differences of how the student has chosen to use some symbols. You can see that we have a key here, or the objects that are drawn up here. We start to see a little more complexity. And then this is an example of a high-rated model. And you see that this one comes from a different test, but you begin to see some of the, we got a protease here, we've got a gate, we've got charges, we've got, different kinds of things or depth of understanding. ATP, getting into some ideas. This is not from this classroom, but it's an example of what middle school kids can generate as the criteria that they're going to use within their classroom. So now they can begin to critique each other's work. Okay, so this is classroom generated ideas that the teachers put up, and then they sort of looked at that. So kids are more capable. What was interesting is we saw some very significant differences between the 2 teachers. And what we also found in analyzing the data is that the majority of the students scored within or above the middle range, showing that students in the 7th grade are capable of creating models that contain mostly appropriate scale, include claims and evidence for their reasoning, identify and include the vital constituent parts, and meet the criteria for a mechanism sketch. Okay, so in the theory of mechanisms, there's a difference between a sketch and another component. How we explained T1 over T2 in looking at the drawings was that T1, as you saw in this would have been a sample from T1. There's feedback being given to the students along the way. And so the other thing that was very interesting for us is that if you did well on mechanism, it explained the largest portion of variance in your performance on the other categories. So if we build mechanisms, right, if we make that as the target, other things are going to follow, is what it says to me, if we get people thinking that way. And so the plus signs indicate things that we're improving. You know, what we found is that with respect to core concepts is that we're doing good things with the plus signs, but what do kids do when they don't know something? Right? They just start dumping. Well, maybe this will work, or maybe this will be a hit. You know, a lot of extraneous information that sort of goes into it. So we picked up on that too and didn't relate to that. So we think that this kind of work has implications for the redesign of formative assessment tests. It has implications for the interpretations of students' use of evidence, and it informs strategies for instruction-assisted development. That's too small to see, but I'll leave the slide set with you, but you can then see a lot of these references. Thank you.
Well, just a moment of thanks again for your coming. As you know, the time is abbreviated, but we want to have a couple of questions, especially from some others who haven't had a chance to speak yet. Let's start here with Janice.
Yeah, so Rick, let's think K-8. So in teaching teachers, to think about learning progressions as ending in a moving target. The variable learning progressions, the sense that you're not top-downing the kids, but that you're looking at a range of what that final hoped for conceptual understanding will be. K-8 teachers are dying from this.
Are what?
They're dying from it because they are, quote unquote, in many ways in K-8 science, glad they're living, assessed every minute, dying to, quote unquote, squeeze it in.
Yeah, doing lots of other things.
And assessed consistently on their scores. So in today's contemporary culture, and I love this work, for me, the real challenge is looking at how we can have some both and thinking. Because you know what? Both and thinking. What I'm trying to say is they can't risk lousy formative assessment. They can't risk it for their jobs. Okay? And so one of the real challenges for the moving target is, in my experience, K-8, we have to give our science teachers a range. This is what the target looks like. This is what we're hoping for. And if it's not going to be absolutely fixed, the scaffolded parameters.
And what's going to complicate your story is it's not going to have the same starting points in each place.
Correct. So the prior knowledge will be different, the cognitive development. But I just wanted to air that as one of the real conflicts that my teachers, when they read the documentation, say, you know, and so I think a lot of our work in science teacher education is breaking through.
Yeah, we've got to start slow. This is a 5 to 10 year process.
Right.
I mean, the states are adopting, and when they say we're implementing, they're not implementing.
Right.
I mean, they're using the word in a way that they want to say we're implementing, but that's very far down the line. And everyone is saying, go slow. Go slow.
Thank you.
Go slow.
Another question? Yes.
A quick question. I want to pick up on one of the things that you said last, which was about what do you do with the extraneous information?
Yeah.
Because it makes me think of Scarmoli and Breider's just knowledge telling. And so if you want to transform it, what would you do? Would you like go back to the sketch and say, talk to the student about it and have them revise the sketches? Or could you talk about that?
But in a summative assessment kind of a situation, you start to say, well, you know, patterns of, but you're right. No, you still mine out the intuitions.
If you move forward and say, taking that nice data and you want to make recommendations for instruction, what would they be?
I'm a big fan of write and rewrite, do and do over. Meet with your, one of the things that a smart teacher learns to do when they begin to know how students are performing is how to form groups for a purpose. Not because it's just the same old groups. It's like, I want you and I want Bobby and Sally to work together. Why? Because Bobby got it and Sally didn't. Or they're close. You know, so when you begin to understand your students well enough, you can begin to cobble together the group work in a way that is beneficiary for the learning, rather than just kids getting together in their self-selected orientation.
Thanks.
I'm afraid to say our time is up, but I did want to say you are a great model of our college. but if you wish to take another one, please.
Okay, hi, I'm David May, I'm over at the University System.
I heard you
of Maryland
speak in Baltimore this
office.
year.
Oh,
What's
okay.
that?
I heard you speak in Baltimore this
Oh,
year.
you did? Oh, great. A question I have is, I'm very glad that you brought up the need for students to be able to make decisions about data
Yeah.
and what to collect and how to design and plan experiments. Because that's something I've been talking about for a long time, particularly since the old National Science Education Standards, which we've been involved in, I'm not sure, which defined, at least in one part of it, inquiry instruction as consisting of not only the interactive engagement, hands-on, minds-on part, but the autonomy part, which the ability of students to be able to decide what to do next and how to decide. That, as you pointed out, I still don't see that autonomy piece being taught very much or emphasized very much.
I'm not sure I understand how you're using the word autonomy. In other words, you're leaving it to them to decide?
Yes, instead of teachers
Would you
saying
leave it
that,
to the individual, or would you want it to be the group?
well, it really depends on the context. I mean, I think,
No, think about that. In other words, if it's a learning situation, right? It's an interesting question because we're starting to challenge the question. Is the assessment of learning done on individuals or not? Can it be done in other manners in which, contribution? And this moves, and I didn't bring this up at all, but it brings us to the 21st century skills kind of an orientation to what people are talking about.
I think students, well, I actually think students should be able to do both. So I guess my sense of autonomy means autonomous from teacher instructions.
Yeah.
But definitely.
Well, one of the things that I've done is been doing that is showing someone else's work.
Right.
And saying, what do you think about this? Because they're not going to feel comfortable talking about their own stuff.
Right.
But man, they'll go to town on someone else's. And then you can see how they're reasoning in terms of, did the person do this right, that right, and why not? What would you suggest they do differently the next time? And it just, it rolls.
I've seen that with the reviewers too.
Thank you, everyone.
Thank you very much. This is our first event. Please look forward to other events we have scheduled. I think the next one is a chocolate event. Is that right, Kate?
Correct.
Oh, sure.
Chocolate.